Okay, welcome back everybody to the last week. And I hope you had a great weekend, although it doesn't look like a spring weekend last weekend. So hopefully it's going to get warmer, hopefully. Now, I just wanted to give you some quick messages about how we're going to organize this week and next week. So you can probably see from the screen here, what I want to do today is try to wrap up the discussion about the variational calculus and Lagrangians, and at the same time say something about the finals which we had last year, just show you the solutions to it and guide you through that, so you get a kind of feeling of things which are important to remember. So that will serve as a kind of repetition. And then I'm going to show you a final example on the variational calculus and how you can use that one on more realistic cases. Then on Wednesday, the final one is going to be available, 8 o'clock in the morning, hopefully, so you can download it. And we will start discussing the final at the same time as we wrap up and go through what we've done through the semester. And then we will use the rest of Wednesday and Friday to actually work on a final. Now, there is also the possibility, if you wish to actually take to swing by here during the finals week, if you want to. So I was thinking that we could actually have some activities during the finals week where we can meet at a regular time. And if you wish to discuss the final project, you can swing by either via Zoom, as we've done all the semester, or just come in person as you're doing now. And I was thinking that we could use the same time slots as we've been using for the rest of the semester, if that fits everybody. And if not, just shoot me a message and we can always have a separate Zoom session. So there's no problem with that. And I'd like to set a deadline on Friday, the 5th. That's also because we have a hard deadline when it comes to publish the grades. There's always some flexibility if something goes wrong, but as long as I can start grading during the weekend, that allows me to wrap up everything for the rest of the semester. And we also started to finalize the grading of the second midterm and also the remaining exercises. So by the middle of the week, you should have hopefully most of the exercises which you've been handing in. Now, one thing which I wanted to say a little bit about is actually the final one, which we had last year, because that allows us to bring up quite many elements of repetition and point to specific topics which are important to keep track of. Things like energy conservation, conservation of angular momentum, conservation of linear momentum. Like in the first midterm, there were many people who got a little bit confused or confused themselves because the linear momentum was not conserved because you have a finite force, and the force is actually the derivative of linear momentum. So if the force is not a constant or a zero, that means that linear momentum is not conserved. So there are many of these kind of small things to keep track of when you're looking at the different types of problems. So I'm going to use the slides now discussing the midterm, the final one, which we had last year. So I'm going to look at that one first. And let me just increase. So you have access to the solution as a Jupyter file. And in that case, we are looking at this famous Lennard-Jones potential. So this is a potential which has been widely used in material science. It has been fitted, so it's an effective potential. There is no kind of force of nature from which you can derive it. It's actually a fitted potential where you'll be looking at the scattering between, let's say, two atoms. And from the way they scatter and the equation you can solve when you look at two-body scattering, you can then parameterize the parameter sigma and this parameter epsilon by requiring that you reproduce experimental cross-sections of given energies. So this is a kind of standard procedure which many of you may encounter when you take a course in quantum mechanics. But the potential now, when we plot it, what we will typically see is that we have a minimum. So it will have a minimum down here somewhere. And now we fix the units and the constant so that this epsilon is equal to 1 and sigma equal to 1. So if nothing is specified in the exercises, then it's often convenient to actually just put these parameters equal to 1, like you did in the first midterm. So unless we specify the values, you should feel free to choose the value which make life the simplest for you. Just keep that in mind. And then you can take the derivative and find the minimum here at this bottom point. So if you, and we discussed this last Friday as well, what happened when, I think it was last Wednesday, because this is part of one of the exercises, what happened when R is larger than 0, no, larger than sigma and less than sigma. And you can then find the equilibrium point by taking the derivative. Remember now that this is you finding the equilibrium point. If you take the derivative of the potential and don't put it equal to 0 and put a minus sign in front of it, then you have the force. Okay, so that would be the definition of the force when you only look at the radial degrees of freedom. So in this specific case, the potential is simpler because it depends only on the magnitude of the distance between two objects. This is pretty common for many forces which we encounter. And the Lennard-Jones potential has been parameterized according to that, because one of the starting points is actually the Coulomb repulsion between two electrons, or the attraction between an electron and an ion. And then this Coulomb interaction is modeled according to the relative distance between two objects. So what you would have then, when you take the derivatives, this is just going through. So if you have time and you want to go through the mathematics here, then you can find the minimum point. And if you put in sigma equal to 1, as we did, this should be 2 to the power of 1/6. And then there are questions about the description of what happens, but I wanted to go back a little bit to one of the things which, so if at the final, if you ask to show that this is a conservative force, so unless you're in one dimension, like we had in the first midterm, where it's actually easy to state that the curl in one dimension has to be 0. When you are in 2 and higher dimensions, if you ask to show that the force is conservative, then you actually have to run through the calculation. So in this specific case, what you need to do then is to keep in mind that it depends only on the relative distance, the magnitude of the relative distance, but that depends actually on the absolute value of the difference between Ri and Rj. So that means that if you now make a transformation to the relative coordinates, which is the distance between Ri and Rj as vectors, then you can think of x, y, and z as the coordinates of the relative distance. And then you would take the derivative with respect to that. And if you go through all these exciting exercises, you would first find the gradient from the potential here. And this is actually not the most exciting, so I'm just stating it. So, but if you are being asked about the force and you are dealing with something which is beyond one dimension, then you would have to set up the force as a function of the gradient of the potential. And then you would need the different components. They would be, this would be the unit vector in the x direction, the unit vector in the j direction, in the y direction, and similarly the unit vector in the z direction. And these are the expressions which you get. They are not the most easy, they're not the easiest one to simplify. So this is roughly what you would set up. And you see now that x squared plus y squared plus c squared is the same as r squared. And you could simplify that one if you want to. And then you need to take the curl. So there is a kind of lengthy and boring derivation. You should feel free to use symbolic manipulations like Mathematica. But what you need to do then is actually to show that the curl is equal to 0. So that has to be shown. If you're asked whether this is a conservative force or not, and it's not unlikely that there will be such a question, because this is about the basics of the forces and the basic understanding of what happens. So I don't think I'm going to make a as complicated problem like this one, but you would have to show that the curl is equal to 0. So that's an important aspect. And with that, you know that the forces are conservative. And when you then calculate the energy, then you should actually show that the energy is conserved numerically, if that is an exercise. Now, one thing with linear momentum, which is also important, is actually that linear momentum is the sum of the internal forces acting on one object and the external one. And then you have the internal one and the external one on the second object. Now, the system in this final, was defined so that the external forces were 0. So there were no external forces. And that means that the sum of the internal forces, if you use Newton's third law, they have to sum to 0. So if you have only internal forces, then the final linear momentum should be conserved. So that's another thing which you should be a little bit careful with, because like in the first midterm, many of you actually got a force which had a finite expression and depended on x. And that means that the force is not constant, and that means that linear momentum is not conserved. So in this specific case, since you only have internal forces, there are no external forces which influence the system, then due to Newton's third law, the force on object 1 from object 2 is the opposite of the one from object 1 on object 2, and then they cancel exactly. And then linear momentum is conserved. So if you have a good hint, if you have an energy conserving force, often what happens then is that linear momentum is also conserved. And then you can do the same thing with angular momentum. And in this specific case, when you have angular momentum, what you end up with is that the force now is defined as you have no external force, so that term disappears. And then you're left with R1 minus R2 with a cross product of F12, which then depends also on the relative distance, the vector. And that means that the angular momentum or the torque has to be equal to 0. Now, there's one thing in this exercise which is a little bit trickier, and that has to do with the fact that when you want to set up the equations of motions for the two objects, you need actually the acceleration for each object. And that means that you need to find the force which acts on a specific object. So that means that you need to take the derivative of this quantity with respect to a particle in position Ri and a particle in position Rj. And when you do that, you have the acceleration. So this expression is the acceleration. And similarly, you would have one term like this for the first particle and one for the second particle. So this is something which is, in this specific exercise, the force has a little bit more complicated expression. But when you are going to do this numerically, there will be a force on every object, like you did for the solar system. You found the force which acts on the Earth, the force which acts on Jupiter, and all the other planets. And then the sum of all these forces is the one which defines the acceleration for one of the specific planets. So if you then scroll down a little bit here, we have now the expressions. So the first thing is actually about making the expression dimensionless. I'm going to skip that one. But when you now set up the numerical part, so let me just run through this. Oops, I have to, let me just restart the notebook. Now let me just run through here. And then I wanted to show you the numerical part here. So there's a scaling of the equations, and I invite you to take a look at it. And in this specific case, we set up a final time, which is just 5, a time step, which is 0.01. We define the acceleration depending on the positions of particle 1 and particle 2 here. And that returns the accelerations for particle 1 and particle 2 here. So this is the acceleration due to the force on atom 1 by atom 2. and then due to the force on atom 2 by atom 1. So this returns the acceleration. Depending on the positions of the two objects, it returns the acceleration for the two objects. And here, what follows is actually just a plain setup. You set up the accelerations, and you find the accelerations of the two particles. We update the positions for particle 1 and particle 2. Then we recalculate the acceleration at the new positions. And then we use that one in the velocity Valère method. So this function which you see here is a function which just sets up the final Valère method. And if you just move on then, and you want to simulate the system, so you can simulate the system for different distances. And so let me just run through here and show you what kind of results you can get. So this is a case when you have a bound motion. And what you will see then is that the object is going to oscillate between a distance 1.5 and a distance which is close to 1.0. So if you go back to the potential, you would see then that we have selected initial conditions where you start here. And then you start here with kinetic energy equal to 0. So you have only potential energy. And you move down to the bottom point, and then up again to the same potential energy and 0 kinetic energy. And then you have a turning point here, which is close to 1 here. And you see that from the graph here, when you look at the potential and you make the plot, what you will see then is something which looks like this. So if you're asked about what kind of behavior you see, this is a kind of comment you should have in the answer, that we have a particle which begins at a specific position in the potential, and then it can, in this case, oscillate back and forth. So this is a kind of behavior which you then would expect if this is a kind of bound motion. So if we are at the bottom of the potential well, where the derivative of the potential is equal to 0, this is a typical case where you would expect circular motion in this case. If you now are in one of these points which are away from the minimum, what you would expect is a bound motion in this case, and the type of orbit would be a kind of elliptical orbit if you were to plot this, as you saw for the solar system. So many of these physical problems which we encounter, if you have gotten a feeling of the solar system and what kind of physics you expect, you can actually take over all these kind of ways of interpreting the system and then look at a similar system like this one. Now, one thing which sometimes, as we have been discussing many times, if you look at the, so let me just run through and look at the energy conservation here. Here's another distance which is a little bit smaller, which then corresponds to an unbound motion. So this should actually, so in the unbound motion, what you would see is that the particle disappears. And that corresponds to a motion where, if you go back to the potential, it would correspond to a position where you are here, and that corresponds to an unbound orbit. And that means that the particle leaves away from the center here, or it would start here somewhere, have a minimum distance to the to 0, and then after some time it would just leave and disappear. And this is essentially what you saw also for the solar system when you had some hyperbolic orbit and you have an unbound orbit. So this is actually me plotting something to a place here which it shouldn't. And then you can look at the kinetic and potential energies. And if you do that, there is always something which is deceiving. And if you now look at the total energy, and the reason why this can be a little bit deceiving is that if you now look at the numbers which you have here, so the energy is a constant, but you see now that it oscillates around a value here which is 10 to the minus 21. So the total energy is a constant, but it fluctuates a little bit around a very small value. And what you will see depends also on the size of your step size in time. And if you now look at the type of motion you have, you see that since the potential is pretty sharp, and this is something you saw also in the first midterm, since the potential is pretty sharp at the bottom, it means that you need many more time steps to compensate for the fact that you're dealing with a numerical solution, and the numerical solution is an approximation. So when you move away from these kind of initial conditions, which can condition these energy conservations, what you see then is that the total energy is basically flat as you move on after some time. So there will be some small fluctuations in the beginning, and this have often to do with the numerical uncertainties due to the fact that you have a time step which has a given value. So if you make this smaller and smaller, then you will see less and less fluctuations. But also what happens is, and you see that it oscillates a little bit here, and the total energy, due to the fact that you have very sharp changes in the potential energy and the kinetic energy, you need actually more points in order to get a flatter curve. So this is something to think of. And sometimes when Python plots it, it gives you the error plus the value. And sometimes you will see something like 10 to the minus 10 plus a number. And what you see plotted then is actually the fluctuations due to your numerical error. So just keep that in mind, because sometimes the plots can be a little bit deceiving. And these kind of fluctuations which you see, they are simply due to the fact that you have a finite size time step. When you make that smaller and smaller, then this kind of small fluctuations which you see in one of the curves, they will tend to disappear. This is an energy conserving problem. So that means that the green line which you see on the slides here, they should always be basically constant. So the small fluctuations have simply to do with a large time step. If you decrease that one, then you're going to get a flatter and flatter curve. So just keep that in mind when you are doing something numerically. So in this specific case, the force is a conservative force. And that means that energy should be conserved. So I just invite you to take a look at the answer to this midterm. No, the final one. And in this case also there's a total conservation of angular momentum because the potential actually conserves angular momentum. When it comes also to one of the exercises this week in homework number 9 is actually the last exercise here. So feel free to take a look at it, and that could perhaps alleviate the solution of the last homework. So I'm not going to repeat everything which is in the slides. I invite you to take a look at the solution to the final from last year. And then on Wednesday, we are going to start discussing the next final, the final for this year. Any questions so far? So I wanted to wrap up the Lagrangian discussion with a problem which is, we've seen already realistic problems like this Lennard-Jones models, but this kind of formalism, which you see the Lagrangian formalism, can be used in many, many different types of occasions. And the case we are going to look at now is back to the harmonic oscillator. So this is going to allow us to repeat something about the harmonic oscillator, and at the same time, bring it in connection with a more interesting problem. Actually, this kind of harmonic oscillations, they've been used to model earthquakes, and especially how a building reacts to an earthquake. So you know that where we live here in Michigan, an earthquake is very unlikely, but if you live in California, it's not unlikely that during your lifetime, you may experience an earthquake. And so the way you build houses, you have different specifications and technical specifications which you need to comply with in order to live in an area where you have the risk of earthquakes. So let's take a quick look at that, and then look at a model which can be solved analytically. So the first case I'm going to set up now is a more general model. And then we are going to look at a case where we have three objects which are coupled and which mimic the way a molecule actually vibrates. So let's take a look at this. So this is a kind of just a way to wrap up and remind ourselves a little bit about the harmonic oscillator as well, which is another topic which we have covered this semester. Let's see, here we go. So the harmonic oscillations and Lagrangian formalism. And we may sneak in some of this on Wednesday. Alternatively, we may just refer to notes, plus the Lagrangian formalism. So there is actually a model for earthquakes. And buildings, where you can actually use a harmonic oscillator. So you could now think of the floors of a building. So ideally, this is a system in 3 dimensions, but we can actually reduce it to a system in 1 dimension. And now you could think of the positions of every floor. So every floor, what we are doing now is that each floor is approximated by a point in the center of the floor. So that's one way of making an approximation here. And if we are using classical mechanics, we often treat objects as point objects. So you could think of now as every floor having a specific mass. So this will be the first floor has a mass m1, and then we end up with a final floor here, mn2 and mn minus 1, and this is the final floor. What you could also think of now is that there is a linear restoring force. So the way we're going to make this model is that every floor is now connected with a spring force. And this is a typical model which is actually used in modeling buildings. So it's not, what you're going to see now is not so different from the basic type of modeling of the structure of a building, which can be exposed for vibrations. So the harmonic oscillator is actually the vibrations around the minimum. So what you could think now is that there is some kind of spring force between every floor. So that means that the first floor is connected to the second floor, and it's connected to ground. So you could think of the first floor having a position. This is the equilibrium position, and this is essentially where we would like to be. And there's an xn minus 1, there's an xn minus 2, etc. And every floor here is now connected with a kind of spring force. So we could now just design that like this. So that means that there is a spring constant with the first floor, K1. There's a spring floor for the second floor. And then we have a new constant for the second last floor. And then for the next last floor, and then the last floor here. We could also think that there is some kind of damping. So when these floors are set into motion and they start vibrating, and this is a typical thing which you would see in buildings which are tailored to actually stand in earthquake, in places where there is a danger for earthquakes, is actually the building vibrate. I mean, if they were static, very static, they would collapse immediately under an earthquake. So you can actually model this type of buildings using a harmonic oscillator. So you could also think that there is a damping between each floor. So this C1 here is a damping parameter, which could be velocity dependent. So you could have a damping, and every floor is now being damped due to a damping force, which we assume can be velocity dependent, like we did when we looked at harmonic oscillations. So everything we did in harmonic oscillations is something we can repeat here. And what we could assume as well is that if you think of this as the ground, the earthquake comes with a force here, an external force, which we could now put up as some constant F0 times some cosine of omega times t. This is one way to model the shock from the earthquake on the building. So then the building will, in a certain time, vibrate up and down due to the shock from the earthquake. You see how we can model? It's not so, it's a very intuitive way of thinking of how a building will actually react to an earthquake. So then the next thing we will do now, since we have just limited ourselves to live in one dimension, in principle, you should now set this up in 3 dimensions, because I mean, an earthquake will obviously be directed in 3 dimensions. It's very unlikely that it will just be coming in 1 dimension. And the building will vibrate in 3 dimensions. And hopefully the most important vibration axis is the one which goes up and down, so that it doesn't vibrate too much to the sides. So now we are just simplifying things. But if you want to make this more realistic, you could now think of setting up a system of equations which also contains other spatial degrees of freedom. So if you now set up the forces here, you could think now of the acceleration on the first floor. So this is the time derivative. So this is going to contain a k1 times x1. And then there is going to be a force between the first floor and the second floor. So that would be an x2 minus x1. And then we decided that there's going to be some kind of damping between the floors. So there's going to be a velocity for the first floor minus the velocity for the second floor. And then we would have this additional force, which goes like F0 times cosine of omega t. And now we are going to, we can decide whether this is an acceleration or just a force. Now we just put it like a force here. But we could think of an acceleration which is different on every floor. And then we would rewrite this in terms of the mass of each floor multiplied with this acceleration due to the earthquake. But let's put it like a constant here. And then you would have an m2 of x, and this is given by minus k2, and x2 are the equilibrium positions, x1 is the equilibrium position, and then we would have a k3. So now it's in contact with the third floor, and then we have a minus c, and this plays the same role as what we saw previously when we looked at the harmonic oscillations. But now we have a system which is coupled, minus x3. And now we have to put in the constants here. So this is a C1, this is a C2, and we have a C3. And then finally, we have the external force, which now is given by an F0. And we're assuming that it's a constant on all the floors, which may not be the best approximation. And you see now that you could continue like this till the final one. And this is an mn of xn. Second derivative, this is acceleration times the mass, so that's the force acting on the last floor. There is a spring constant of xn minus 1. And then I have minus, and I have a cn minus 1. And in this case, this just connects with the second last floor here. And then we have this applied force, F0 of cosine of omega t. Now, this is a problem, and since many of you have only this semester started to look at linear algebra, this is actually a problem you can rephrase in terms of a matrix vector multiplication, and then solve it using linear algebra methods. Because what you would do then is actually to define a vector. So how many of you have done linear algebra and solved linear equations with linear algebra? Some of you have done that, not everybody. But just think now of you. So I'm just going to say this without actually going through in more detail. But I just wanted to show you how you can set up the system. So you would define a vector now, which contains all the positions from x1, x2, down to xn, the last floor, you would define a matrix which contains the masses. So you would have an M1, M2, down to Mn. And then you would have zeros. So you have nothing along the diagonals. And then it's common to define what is called a stiffness matrix, which contains all these constants. And the first one is K1 plus K2. And then I have a K2 here, and a K2 here, and the rest of the elements are zero. And then I continue along here, I would have minus K2 plus K3, and then I get a K3 here, and then zeros for the rest, a K3 here, and all the other ones are zeros. And this continues along the diagonal. You can then define a matrix for this damping, which looks similar. So what you would get then is a problem which you could rewrite in terms of this matrix M multiplied with the vector of the second derivatives, which contains the accelerations. And you could actually rewrite this in terms of a matrix given by this K multiplied with a vector X. And then you would have a new matrix C, which contains these damping factors multiplied with the first derivative. And then there will be a new matrix which contains the force here, which I write like an F bar here. So this is a problem which you then can rewrite in terms of a linear algebra approximation. And you could actually solve it by using linear algebra method, which means that you would have to do some matrix inversions. I'm not going to show you how you can do that, because I mean, this would be well beyond what many of you have seen. But this is the way you would actually treat many of these harmonic oscillations when you have coupled systems. What we are going to do now is actually to specialize to a system with three coupled objects, which can be solved analytically. And that's where we're going to use the Euler-Lagrange formalism. So we are going to, instead of looking at this building, which oscillates back and forth, and solve the linear algebra problem, we are going to just set up a problem which we can solve by paper and pencil. And the case we are going to look at is something which is called a linear model for a molecule. So our example, and this is where we are going to set up the Euler-Lagrange equations. So this is a linear chain, and you will actually see that this is a popular first order approximation. And we are going to use this one to describe the carbon dioxide molecule. So what you could think of now is just setting up a coordinate system, and this just moves in the X direction. And you would now have an oxygen atom here. You would have your carbon atom here. And then you have another oxygen atom here. Now, I'm going to use something which will make the chemist in you, if somebody has taken a course in chemistry, cry out, because I'm going to assume that the mass of the carbon atom is twice as heavy as the oxygen, which is not correct. And I'm going to do that because that's going to simplify the mathematics, okay? So don't give me away to a chemist, actually. So we assume that this has a mass 2m, this has a mass m. And what we're going to do now is to look at the way this system behaves, thinking of these as coupled harmonic oscillators. And that this carbon dioxide molecule is going to vibrate in the X direction around an equilibrium position. And people can actually, from experiment, they can look at these so-called vibrational modes. Now, the benefit of this system and the simplifications we are doing now is that we can solve this analytically. We don't need to revert to setting up a linear algebra problem and then solve the linear algebra equations numerically. So that's the main benefit here. And what we're going to look at now is a system where we would have a distance here. This is the equilibrium distance, which we call x1. We are going to have a new equilibrium distance out here, which we call x2. So that's the coordinate of the carbon atom, and that's going to vibrate around x2. And finally, we have the last position, which is the one for the oxygen atom here, which we call x3. So this x1, x2, and x3, you see now how this mimics this model which we made of the house, which vibrates in the x direction. You could now think of these atoms vibrating around their equilibrium positions. And the excitations energies of a molecule like carbon dioxide can actually be approximated to a first approximation with such a model like this. It doesn't deviate too much from experimental data or experimental observations. So what we are going to do now is to set up the Lagrangian. So we are assuming now that there is a harmonic oscillator potential. So we can set up a Lagrangian L, which is given in terms of the kinetic energies. So we would have 1/2, and since the masses are all put the same, and this is one of the simplifications which I plugged in here. So we have the derivative of the x1, which is the velocity of x1. And in this case, we have 2 times m, and then we have x2 here squared. And then we have the final kinetic energy of x3, the velocity x3 squared. And then we have to subtract the harmonic oscillator potential, which now goes like k divided by 2. And in one case, we have x2 minus x1. It doesn't matter where we have x2 before x1, and because this is squared. And then we have minus 1/2. And then we have k. And then we have x3 minus x2 here, squared. So this is the Lagrangian. And it's pretty straightforward to see that this is the way it should look like. And then we can use Euler's Lagrange equations and find the equations of motions for x1, x2, and x3. So what we would do next is simply to use the Euler-Lagrange equations, and then we can find the equations of motions for the three masses which we have. So what we would do then is simply to set off d of L, and then a d of x of I, minus d dt of dl of dx of I derivative with respect to time. And we want this to be 0. So this is the equations which we are going to set up in order to derive the equations of motions. So if we do the first one, so let me just give you the answer here. So the first one gives us now m, and since the masses are the same, we just use m. We have the second derivative, and this is equal to minus k times x1 minus x2. And it shouldn't be that difficult to see that when you take the derivative with respect to x1, then this is the expression which you should get. And so if you take the derivative here, you get a plus, and then you move it to the other side, and then you have the same equation for the derivative there, and then you end up with that expression, which you would also get if you were to look at the figure and set up the forces, right? So if you go back and look at the forces which you have, and you take the first object, there is a force from object 2, x2, and that has to go like minus k times x1 minus x2, because that's the distance, or actually the force which acts on the first object from the second object. And then you would continue along these lines, and you can find the equation for the second one. This has 2n times x2, second derivative, and when you take the derivatives, you get minus k of x2 minus x1, minus k of x2 minus x3. And you can rewrite this as a minus k, and then we have 2 times x2 minus x1 minus x3. And the final one for x3 is simply going to be minus k times x3 minus x2 here. Now, this is a problem which you see immediately is a couple problem. If you now look at the equations here, you will see that the equation for x2 depends on x1 and x3. And the equation for x3 depends on x2, and similarly the one for x1. So that's a kind of hint that maybe we cannot find an analytical solution as the equations stand now, because they're coupled. As soon as you have coupled differential equations, that's often a hint that either we can rewrite them, like we did for the Earth-Sun case, where we rewrote things in polar coordinates and could then solve it analytically, or you find some smart substitutions, or you simply have to solve it numerically. So if you look at this case with a house which is vibrating, that's a typical example which you would have to solve numerically. Here, however, we can perform a trick and change the variables. And by changing variables, we will be able then to find an analytical solution by a smart change of variables. So I wanted to show you that one, and we're going to wrap this up on Wednesday before we then summarize and discuss the midterm. So what you could do now is to define a new variable, which we call for Q1, which is simply x1 minus x2. And then we define a new one, which is Q3. And that's going to be given by x3 minus x2. And we are going to define another variable, which we call for x, which is simply the center of mass, x1 times m, plus 2m times x2, plus x3 times m, divided by the total mass, which is 4m. So this variable here, since we have the same mass, and this is one of the reasons why we took the same masses, is that makes life a little bit easier. So this is the central mass position, plus 2 times x2, plus x3, divided by 4. And what we can do then is actually to rewrite the variables in terms of these x1s and x2s in terms of these new variables. So I can actually rewrite x2 in terms of this quantity. You see that easily, 4x minus x1 minus x3 divided by 2 here. This looks a little bit complicated, but the benefit is actually that when we plug this into the Lagrangian, things are going to simplify. Minus Q3 plus 4 times x divided by 2. And then we have x3, which is going to be 3 times Q3 minus Q1 plus 4 times x divided by 2 here. Then, when we set this into the Lagrangian, this is going to simplify considerably. So let me just give you the answer. And then on Wednesday, we are going to show the final solution. And that's just going to take us 10 minutes of Wednesday's lecture. So this is going to be given by K kinetic energy minus potential energy. The potential energy, V, when you do this transformation of variables, is simply going to be K divided by 2 of Q1 squared plus this Q3 squared. So we can actually simplify the potential energy in terms of just these variables. And you can see that immediately because we define Q1 to be x1 minus x2 and Q3 to be x3 minus x2. And you see now that in the potential energy, we have a term here, which is Q1, a term here, which is Q3. This is the same as Q3. And this is again the same as this term Q1. So that means that the potential energy can then be rewritten in terms of these variables. The total kinetic energy is, on the other hand, going to be a little bit uglier, but the final equations are going to be pretty simple to solve. So this is going to contain, and just setting in the substitutions here, a Q1 squared plus a Q3 second derivative squared. And then it's going to contain a minus m of Q1 derivative of Q3 derivative divided by 4 plus 2 times m times this central mass position, the time derivative square. And then what we're going to do now is to use the Euler-Lagrange equations on this Lagrangian. And if we do that, we're actually going to be able to find an analytical solution. So when people have seen this type of equations, they often been trying different combinations of variables. And by a little bit of experience, you may see that there are specific combinations which can lead to a separation of the variables. So the neat thing here by this trick is that you can actually solve a problem with 3 objects analytically. But in general, you would have to go back to what I put up for this kind of building which vibrates. You would actually have to solve this numerically as a set of linear algebra equations. And that's the standard way by which these type of problems are actually being solved. So for those of you who have taken a course in linear algebra, you've probably seen the solution of differential equations in terms of matrix vectors problems. And you've probably seen something like Gaussian elimination. Does that ring a bell for those of you taking linear algebra? That's the standard way by which you would solve this type of equations. Or if you're lucky, you can invert a matrix. Okay, so on Wednesday, I'm going to sneak in 10 small minutes to solve that problem. And then we're going to repeat and discuss the final midterm, which will be the main goal on Wednesday. Good night. Have a good one, guys. Feel free to hang around, ask questions if you have.